Okay. We have an extra special treat for you. One more talk. I'm going to invite to the podium Rudy Rossetto, and he'll be presenting on, this is an addition, sorry, I have the title, ICT Solutions for Monitoring and Operation of Managed Aquifer Recharge Schemes. I think it complements the first talk we had today. Jana.
Thank you. I'm just filling a hole, so yeah. Hopefully I will not annoy you so much. So I'm talking you about the power of ICT solution for monitoring and operated managed aquifer recharge scheme, and it's basically a follow-up of first presentation of today. Yes, as Giovanna say, in Italy we have so far 40 experiments on managed aquifer recharge. It was unauthorized till 2013, and now licenses is regulated from 2016. One of the key points of the new regulation is that the dedicated monitoring system is required. Is required during the design phase, and we have to go monthly for getting hydrodynamic and hydrochemical and biological data, but then is more extensive and large during the operation phase. During the operation, there's still monitoring to be done to evaluate the effectiveness of the scheme and the impact for detecting potential deterioration of groundwater, but the law is also demanding for high frequency and continuous first alert monitoring, at least at the upstream recharge point, to guarantee what? To guarantee that we are able to stop recharge into our recharge scheme. So we cannot think of something that is human managed, like I go and make it on-off, but we have to think about of a SCADA for managed aquifer recharge, and that's what I'm going to show you that we did. We use this Rossetto double-stage infiltration basin. First stage is settling pond, and the second one is the real infiltration, and this is the basin as you were seeing before in full operation. So, for setting up this operational and monitoring scheme, we made massive use of ICT, and we developed an ICT architecture, infrastructure that is based on three main functions. The first function is based on sensors, data gathering and management for the operation of the pump. You know that ours is a rainwater harvesting scheme, so what we do is that we gather excess flow from the river and we bring it into the infiltration basin, okay? So we have to manage the pump for this diversion. The second function is that we have to monitor the impact in the groundwater. So we have to see that the recharge is not causing alteration of groundwater chemistry. And the third one is that we need to have a unit that gather this, all this data, analyze them, feed back the pump unit, but also store the data and send the data to us remotely. That we, for example, my university is in charge of the monitoring, but we are 100 kilometers away from the scheme. So that's the main issue. And this is the monitoring scheme at the plant. So I don't know if laser works.
The other thing on the podium.
Okay. Thank you. Yes. Okay. So this is the diversion pond. And we have a mass spectrometer here near the diversion pond. We have a set of sensors for level, electrical conductivity and temperature, this triangle all around here, and then a traditional multiparametric probe here, okay? I will give you details of all these sensors I'm showing here in the plant now. This is the full architecture of the infrastructures, yeah? The sensors might be connected using the long-range wireless communication system, the LoRa, okay? And they wake up every 15 minutes, get the data, and send it to the control unit here. The control unit make comparison with the threshold we set, okay, and then send signals pump or not pump, okay? And the same applies for the mass spectrometers. It wakes up every 15 minutes, monitor the quality of water, sent to the control unit. There is a check here, and then a signal is sent back to the pump or not pump based on the quality of water. It's a bit different with the multiparametric probe into the aquifer because this doesn't allow the pump to pump or not to pump, but sends us a signal if any of the parameter is a bit different than the average range that we have been detected during the pre-operational phase. And then we have, let's say, 24 hours to go and to grab a sample and bring it into the lab. So we use a PostgreSQL database to store all the data, so it's an open source solution. And the radio module is a ultra-low power STM microcontroller. We use a LoRa transceiver. We have a plus 20 dBm output power and we work with 869 megahertz. And it's a really low power consumption because it works with 10 milliampere during signal gathering, but lives with 25 microampere when it sleeps. And I can tell you that because we want to avoid vandalism with solar panel, we put battery there, like 20 volts, 40 milliamperes, traditional car batteries, and they last a whole year of recharge. This is how the control panel looks like. You can access it with TeamViewer or any desk application with my mobile. I can see here from Madrid what is going on at the scheme. And you see it's all green. It means that we are allowed to pump. Okay? When we are not allowed to pump, some of these parameters get red, and a pump will not work. Which are the controller we set? The first one, all these are decided according with water-related authorities, the Health Organization, the Environmental Protection Agency. The first one is related to the minimum ecological flow of the river. We agree with the authority that we can pump just over the minimum ecological flow. So to pump, the signal must be get water for recharge only if the discharge of the river is over the minimum ecological flow. This is monitored through hydraulic head level, okay? If this level that is gathered at the sensor from the hydrological service of Regione Toscana is over 0.47, the pump starts. If it goes lower, stops, and we have no recharge. The second signal is based on all these parameters: turbidity, nitrate, TOC, DOC, color, UV 254. It's a mass spectrometer as a scan spectrolyzer, and more than this parameter, we can get the spectral signature of the water. You see in this picture, you have the wavelength, and the absorbance per meter gather every 15 minutes. Here we are in a descending phase from a flood event, so the water is getting more clean, and with this tool we have seen that we have also to stop recharge when the flood water gets very with a lot of turbidity in, not just because we risk to clog the plant, but because with high turbidity we have a high content of iron and manganese, very high content. So we stop we decided to stop when the river level goes over 1 meter. Of course, flood is a transient event, so it lasts usually no more than 24 or 36 hours, okay? So we avoid this for this time. Then we have another problem, that is a basin, and we don't want the basin to be overflooded, okay, so that we get water out. So we set an hysteretical cycle for which there is a couple of sensors in the basin, and when the top level that we set is reached, the pump stops. Then the basin, the water infiltrates, the water goes down. When it reaches another level, which is the bottom level we set, basically we have a cycle of 6-7 centimeters, the pump starts again. Okay, and this is a cycle of about 3 hours, and it takes 1 hour and 1 hour and 15 minutes to go down, and 1 hour and 45 minutes to go up. So it's not linear process. Yeah. And then we go for monitoring the groundwater, and we have a traditional head temperature and electrical conductivity sensors, and then this multi-parametric probe hydrolab, where we monitor temperature, electrical conductivity, pH, dissolved oxygen, and ORP. Yeah, these are the kind of data graph we can produce, and these are graphs that we get real time. I'm finished. And so to go in conclusion, in our opinion, having 1 year of experience after we are managing this plant in this automated way, ICT can be a great light in MIR schemes. We will put new sensors in operation in the schemes, also because the whole scheme costed 300,000 euros. So the bulk of the cost, except small excavation, is the monitoring infrastructures, the hardware and the software part. And for example, the spectrolyzer mass spectrometer, it costs something like 33,000 euros. And we want to put another one in the groundwater this time. We want to put another one or a couple of hydrolab sensors, but in our opinion, it makes sense because we need to start thinking about managed aquifer recharge not only as intentional, but highly monitored, because this increase confidence in the authorities and in the general public on this kind of schemes. And I was saying this morning in another talk that if in a country like Italy, where we have just 2 authorized plants, we start polluting an aquifer, this will mean that for the next 30 years there will be no more recharge of aquifer. Yeah. Automation and ICT is still demanding in terms of operation and maintenance. This because sensors may stop working, and also the control unit, and you have to go there, take all, and bring it to the lab. And anyway, another very good thing is that you get a large data set, and this allows to get new insights on classical MAR-related research issues, not just from the lab, but from a real case studies. We're going to drill another 10 piezometers around to investigate better, for example, the efficiency of the scheme. And so I think this is a good thing, and if any other institution wants to come and use this plant for experiments, it's an open lab. We are willing to host you there. I take the time also to announce the forthcoming 2nd edition of the Life Reward Summer School in September. Also this year will be digital water management and natural-based solution in coastal areas at Scuola Superiore Sant'Anna in Pisa, Italy, and we will have a scholarship available. If you are interested, please come and approach me. Thank you.
Excellent. Really nice talk. Excellent. Let's get some questions from the audience. One here. And for all those students, summer school in Italy sounds pretty good, doesn't it?
Thanks for your presentation. I was wondering, how often do you go to the site for calibration of the sensors or cleaning of the sensors?
So we go every month because we have also to do discrete monitoring. So when we see that some sensors needs to be recalibrated, we take it to the lab and then we do it. Okay. Yeah, it depends. You see it because if you start seeing a trend, the first thing you do, you take the energy off of the sensor. you restart the sensors. Then you see the new data you are gathering. If they start again to go, usually if this, the groundwater quality is that, for example, you will go again with that. If it is not, you will restart from another level, okay? From another value. Yeah.
Thank you.
Does the mass spectrometer have a automatic cleaning on it? It's optic, is it?
The spectrolyzer has a
Spectral.
compressing unit to clean the eye. That
Okay.
has to see. Yes, yes. It works every 15 minutes. But
Yeah.
in summertime, when we don't have water, we have to take it off.
Yeah.
Because with very little water, it becomes very full.
Yeah.
And there might be the possibility that algal film develops, and then, so it's better prevention than action.
Sure.
Yeah.
Okay. Another question? Anything?
Coffee break is coming.
Yeah. Okay. Well, thank you so much.
Thank you.
Excellent talk. Do you have housekeeping? No? You're okay? So I think we're done for the day. I challenge you all in 3 years to keep working on monitoring systems and all that interesting stuff we can learn, particularly with 5G coming on. And just a couple housekeeping things. At 17:30, we have the ISMAR Commission Plenary. That'll go till about 7 o'clock. And then, of course, for everybody that has tickets, and hopefully everybody does, at 8:30 tonight is the ISMAR Gala Dinner, which is, I don't have the name of the place it's at, but I'm sure, yeah, if you have a ticket, you know where it's at. So, and thank you all for coming, and have a good night. Thanks.